Alright guys, today we're going to be talking about partial pressure, or how much pressure a part of a gas exerts and contributes to the entire pressure of the gas within the container. So a lot of times we don't have single element gases or single compound gases. Very rarely in a container do you have pure oxygen or pure hydrogen. What you most likely have is a mixture of several gases. For example, our atmosphere, even though it has oxygen in it and several other gases, it's predominantly nitrogen. So what do we make of pressure when we have a lot of different masses and different kinds of molecules all competing in the same space? So what I have here are 3 containers filled with 3 different gases. They each have a different pressure. So let's say that this one has a pressure of 600 kilopascals. Let's say that this green one has a pressure of 450 kilopascals. And that this orange one has a pressure of 300 kilopascals, kPa. All right. Now, each of these have their own individual pressure based on their mass. We're going to say that they're all in the same volume and that they're all at standard temperature and pressure. So at the same standard pressure, temperature, and volume, they each have a different pressure because of their mass and the number of moles in the containers. What would be the pressure if we were to mix all of these different gases into one container? If we were to have one large container with all these gases bouncing around? Well, all we have to do is add up the partial pressures, right? The pressure that each part of the gas would exert, and that would equal the total pressure of the gas, 1350 kPa. All right, so that is partial pressure. You have different gases mixing together, each exerting their own part of the pressure, and that gives you your total pressure. So if we were to have all of these in one container with different elements in there, you would add together the partial pressures and have about 1350 kilopascals of pressure. So let's see this in action with a problem. All right, in this problem, we're going to be looking at how the molar makeup of a gas is going to affect the pressure. So the problem here is that a 10-liter vessel, we have 10.0 liters, contains 2.5 times 10 to the negative 3 moles of hydrogen, 1 mole of 1 times 10 to the negative 3 moles of helium, and 3 times 10 to the negative 4 moles of neon at 35 degrees Celsius. So there's another useful thing, 35 degrees Celsius. All right, and let's go ahead and write out the 3 moles that we're dealing with. So 2.50 times 10 to the negative 3 moles of helium. We have 1.00 times 10 to the negative 3 moles of, what is that? Oh, that's helium. Sorry, this is hydrogen. And then lastly, 3 times 10 to the negative 4. And if you notice on neon here, they like to do this a lot where they put the biggest number in first. And so you see, oh, okay, 3, so there's the most, that one has the largest number of moles, but then they put on the scientific notation that it's an order of magnitude smaller or bigger. So watch out, even though this is the biggest number, it's actually the smallest quantity. All right, So that's one way they try and trick you. All right, and we have to find the partial pressures for each. So A is going to be partial pressure. And then we have to find the total pressure. All right. So let's go ahead and get started. Now, we've already kind of seen problems like this where we have a temperature, we have a volume, and we need to find a pressure. The quickest way to do this is to use the ideal gas law. So ideal gas law is PV equals nRT. We're going to rearrange that since we already have a volume, 10 liters, and we don't need to solve for it. We just need to solve for pressure. We're going to divide that over to the other side. So we get pressure is equal to moles times R times temperature divided by volume. All right, so let's go ahead and start plugging in some variables. First off, N, the amount of moles. Well, we have that given to us. So for hydrogen gas, it's going to be 2.50 times 10 to the negative 3 moles. Then we have R. R is going to be 0.08206. And then remember, R has those complicated series of units at the end. It's going to be liters times ATM divided by moles times Kelvin. And that brings us to temperature over here, which needs to be in Kelvin. So to convert any temperature from Celsius to Kelvin, you just add 273 to your temperature. And that is going to get us to 308 degrees Kelvin, so 308 K. All right, lastly, we need to divide all of this by the volume, which is just going to be 10 liters. 10.0 liters. And let's take a look at our units and see what cancels. We have moles canceling here, liters canceling, and Kelvin canceling, leaving us in atmospheres. So our pressure for hydrogen is going to be 6.32 times 10 to the negative 3 atmospheres. Right, so that's for hydrogen gas only. All right, we're going to do the exact same thing for helium and neon. The only thing that changes is the amount of moles. Right, so we're going to change this number here for each of these, but everything else stays the same because we're not moving containers, the temperature's not changing. So we just need to get the partial pressure for these three gases by switching in the amount of moles. All right, so I'll give you a second to get that started while I clear out some space, and we get on to the second part of the problem, calculating the total amount of pressure. All right, so for helium, you should have 2.53 times 10 to the negative third ATM. For neon, you should have a pressure of 7.58 times 10 to the negative 4 ATM. And for hydrogen, we already calculated it out as 6.32 times 10 to the negative 3 atm. All right, so these three pressures, all by using that same process, the same ideal gas law, right? And now we have to find the total pressure. Well, all that's going to be pressure total is going to be equal to the partial pressure of hydrogen plus the partial pressure of neon plus the partial pressure of helium. All right. So if we were to add these three numbers together, we would get the total pressure of the gas. Now, just to avoid confusion with the scientific notation, the book removes the scientific notation and does it in regular decimals. So if you want to do that, that is fine. We're going to get 0.00632 atm. All right, that's for hydrogen. We're going to add 0 is first. We're going to add 0.00076 atm, and lastly 0.00253 atm. All right, so adding all of those together gives us a total pressure of 9.61 times 10 to the negative 3 atmospheres, which is going to be our total pressure. All right, so we got one more problem to go over, and then we can jump into the homework.